We are still talking about compact sets, and my goal for, I don't know if we're going to get all the way there today, but compact set, I will say in Rn, are closed and bounded. This is the Heine-Borel theorem. Closed and bounded. I had a professor in grad school who he told us a story about when he was in grad school, like in the 60s or something. He was at some Vietnam protest, and he and his friends had a big sign that said "Mathematicians for Peace," and somebody walked up to them and said, "Are you guys really mathematicians?" And he said, "Yeah." And he said, "Oh yeah, well, what's the Heine-Borel theorem?" And he said, "Compact, or in Rn, a set is compact if and only if it's closed and bounded." And the guy said, "Oh, all right." So that's what it takes to prove that you're a real mathematician, apparently. Compact sets in Rn are closed and bounded. So this, I hope that over our discussions of compact sets, you have gotten this general impression that not compact, to show something's not compact, you use an open cover that kind of approaches the boundary, or an open cover that goes on forever, like that sort of bullseye type picture that we were using a couple times ago. That's going to work as long as the set is that's how you would show something is not compact, and that will work if either the set goes out to infinity, that is, it's unbounded, or if it is missing some of its boundary, that is, if it's not closed. So I hope you have some kind of intuition for this. So this is sort of where we're headed. You saw a proof of this in real analysis class, but that was only in R1. I would like to discuss this in other RNs other than n equals 1. But anyway, before we get to this, I want to say a few more basic properties of compact sets. And in particular, I wanted to talk about what happens when you start with compact sets and kind of recombine them into creating new sets by doing things like unions, intersections, that sort of stuff. So I thought we could start off. I have 4 questions concerning compact sets and recombining them with one another. So if, let's say, A1 and A2 are compact, I hope you remember, that means any open cover has a finite subcovering. Is A1 union A2 compact? I want to think about these questions. What about A1 intersect A2? What about A1, the product, A2? And one last one is if A is compact and B is a subset of A, then is B compact? All right, these are 4 different things. And I would like to briefly discuss each of these, but I thought maybe I could give you a few moments to try and think about this on your own. See if you can tell what the answers are. I mean, you don't have to try and prove them, but do you think they're yeses or nos? And I'll give you a hint. One of them is a no, and the other 3 are yeses. So I would like to give you a few moments to think about it. Maybe I'll walk around and see how you feel. Talk to your friends and neighbors if you like. I will say, well, I'm not going to write it, but one of them, the answer is no. I would suggest you just kind of play around with some examples. If you want to draw yourself a picture of a compact set generally looks like it's closed and bounded. So that's how you should think about it. I'll give you a few moments.
This makes sense because of the intersection is empty. Yeah, okay.
Yeah, right. This is
The intersection. Intersection of close.
Would the intersection is empty, would that be,
Yeah.
that's not closed, right? Because that's open.
yes, not all yes.
Sure.
Those two pieces you're right.
But then,
Empty is open, right?
but empty, the whole thing is closed. This one, the intersection.
Thoughts? Yes, no, yes. Some of those are
Okay.
yeah, that intersect. Do you have an idea for the intersection of it?
Well, we're like it's empty, but then the negation of empty is the whole thing. It just opens. Oh my God. I don't know why.
Yeah, the empty set counts as compact. So yeah, if the intersection is empty, yeah. Because the empty set can always be covered by finally many things, like zero
Yeah.
things. So it's empty set is compact. Any more thoughts?
I think maybe the you can always just push.
Yeah, I don't.
Yeah.
I'll give you another minute and then we can talk about them.
Maybe the lower one is,
This is a good idea. Although,
actually no.
if you're asking is
No,
it
never mind.
compact, that means you begin with a cover of B.
No, I have no idea.
And then you have to show that there's a finite subcover of B. But B is smaller than A, so if you have a cover, if you start with a cover of B, it's not necessarily also covered with it. There's some.
Does B necessarily have to be closed if it's a subset? How?
Yeah, I would think really the only picture that's easy to draw would be if A1 and A2 are two integrals, then the product of draw one of the x-axis minus
I know.
the product is like a box.
Yeah.
Because the union of could be a point set not related to them.
Yeah, the union.
That's like the last one.
All right, let's try and talk about these. I see some good thoughts as I was going around. The first one, is the union also compact? The answer to that is yes. Actually, that's going to be one of your homework problems this week. But I will say a few words to get you started. So what you should be thinking about is something like, if I have A1 over here and A2 over here, maybe they intersect, maybe they don't. It doesn't matter for this one. But I'm considering the union. I'm asking, is the union compact? That means you should start with some covering of the entire union and then see if you can make a finite subcovering. So I start with a cover of the union, like this maybe a big old guy over here. I missed the spot. All right, there's a covering of the union. Can anybody say, does this covering of the union have a finite subcovering? I see somebody. Why do you say it does?
I'm thinking because all of the open covers of A1 and A3, if you take the union of them, like they have finite subcovers individually. So
Yeah, right. A1 is compact, which means all the ones that cover A1, you can do that using only finitely many. And A2 is also compact, which means all the ones that cover A2, you can do that using only finitely many. And so that means overall, you can do it using finitely many. You take all of these ones plus all of these ones, but that's still finitely many. You don't need infinitely many. So that's that's what you should say basically for this one on the homework. Okay, so that was a yes. The second one is a little bit more tricky, but this one is also a yes. The picture for that, well, really it's a similar picture, only the problem is now we assume there is some intersection, and I want to know, is the intersection compact? That is to say, if I have a cover of the intersection, so I begin with a covering just of the little part, does that covering have a finite subcover? Now, just because A2 has a finite subcover doesn't necessarily mean this part of A2 has a finite subcover, which is kind of what you need to say. So how do you demonstrate that these guys themselves have a finite subcover? And this, I will just say, is less obvious. And in fact, it's not always true. I said the answer is yes, but actually this is true when the whole space that you're in is Hausdorff. And I don't want to get into the details of this, but this one is true when it's Hausdorff, which is basically, I mean, most examples that we consider of topological spaces are Hausdorff, which is why I say the answer is yes. But the idea here is, if it's also Hausdorff, that means that I can start with this cover of these guys and then additionally put sets around every point of A2. And since if we assume it's Hausdorff, I can make these sets not intersecting with these sets. And then I can also put sets around every point of A1 so that they don't intersect with the blue ones. And then the fact that each of these has a finite subcover means I will get a finite subcover of the blue ones. But that only works if it's Hausdorff, but it does work if it's Hausdorff. All right. That one is maybe the most complicated of these, and I don't want to get into the details of it, although it's not so bad. All right, so the next one, the product. As I was walking around, people seem to think the product should be also compact. Certainly, this one is harder to say, but certainly from the point of view of closed and bounded, we've already said that the product of two closed sets is a closed set, and the product of two bounded things is also bounded. So from that point of view, if A1 and A2 are each closed and bounded, then A1 cross A2 should probably be closed and bounded also. So this one is a yes. That one actually I do want to talk about in a little bit of detail. But let's just say before we get, that's yes always. It doesn't require Hausdorff or anything else. And then the last one. Apparently this is the no, since I said one of them was a node. Anybody have a counterexample? Actually, I saw one person who had a counterexample. What do you say?
The closed circle and then the open circle.
Yeah, how about, so here, could I go one dimension lower just because it's easier to write? Let's say let A be just a closed interval, say -1 to 1, and B be the same but an open interval, all right? An open interval is not compact because it's not bounded. I mean, it's not closed, it is bounded. This one is bounded. So in this case, A is compact, B is not. And so it's not true. Even though this one, I feel like that one kind of feels like it's true, just because if A, the picture for that one would look like just something like this. A is bigger, B is on the inside. And I feel like if you have if you can always make finite subcovers on the big thing, then certainly you can always make finite subcovers on the little thing too. Actually, it's not true. Why is it not true? It's because B may have weird covers that somehow like approach the boundary of B, which are not an issue in A because they don't approach the boundary of A also, they just approach the boundary of B. So weird things can happen for subsets. That's what I'm saying. So the answer here is no for that one. But this one also I want to talk a little bit about in a little bit more detail. But anyway, can we talk first about products? So I'm going to write that one as a theorem. And I want to give you some little idea. This is like a fake proof. This is not a real proof. But just because products are in my opinion, kind of harder to think about than the others. It's harder to draw a picture and so on. But anyway, I'm going to write this as if A1 and A2 are compact. This ends up being a useful fact in our Heine-Borel theorem, which is why I want to talk about it in a little bit more detail. If they are compact, then A1 cross A2 is compact. All right. So the picture that you should have in mind is something like A1 and A2 are sets that you're going to take the product of, which the only really nice way to draw a picture of that is if A1 is some kind of set in the x-axis and A2 is a set in the y-axis. And then the product looks like some kind of a box. In this example, it looks like this. All right, this is A1 cross A2. Of course, including the stuff on the inside. This is what a product will typically look like. And like I said before, from the point of view of closed and bounded, if this guy down here is closed and bounded and this guy is closed and bounded, that means automatically this box will also be closed and bounded. But I don't want to think in terms of closed and bounded. I want to think in terms of open coverings. To show A1 cross A2 is compact, so I'm going to give you like a sort of a fake proof. What I'm about to say is not quite a fully legitimate proof, but it's somehow close. My fake proof would be you begin, as always, to show something is compact. You start with some open cover, and you have to find a finite subcover. So I'll say let O be an open cover of A1 cross A2. So on the picture, that looks like, you know, a bunch of sets like this that cover the whole product, the whole box there. I might have missed a few points. All right. Now, somehow we have to use the fact that A1 is compact and also A2 is compact in order to find a finite subcover of this business. The standard thing to do in a problem like this would be to somehow look at these blue sort of things up here and shove them all down into A1 by the function which just takes, this is like points of two coordinates, and you just ignore the second coordinate and take only the first coordinate. That would project them all down into this part, and they would end up looking basically like this, right? Only they're sort of all flattened out this time. But if you shove them all down into A1 by the function, you know, f of x comma y equals x, that just ignores the second coordinate and gives you the first coordinate, you get a bunch of little sets like that. So my fake proof, this actually works out very most nicely if we assume, and this is not really a good assumption, this is what makes the proof slightly fake, assume that each set in the cover looks like something like a U cross a V. All right, really, all of those sets, the blue circles here, I'm just gonna imagine like they are actually themselves little products of a set from A with a set from A1 with a set from A2. They're not necessarily going to be that, but these kinds of sets make a basis for the product topology. So these things, you could shrink them down to get sets that always look like this. Although when you shrink them down, they don't quite cover the whole thing anymore. That's why this is not a real proof. But anyway, if we assume each set in the cover looks like that, then if we only consider the first ones, the first half of it, the U's, actually, those would make a cover of A1. The U's make a cover of A1. This is what I meant by shoving them down here. If you just like ignore the second coordinate and only think about the first coordinate, they make a cover of A1, which has a finite subcover because A1 is compact. So only finitely many U's are needed, right? That's because A1 is compact. And then similarly, you could send them over the other way into A2 by ignoring the U part and considering only the V part. So I can also say, for the same reason, also the V's make a cover of A2, so only finitely many V's are needed. And that means, put them all together, you only need finitely many of these guys in the product, because you only need finitely many of the U parts and finitely many of the V's. And so, of all the sets that you started with, you only need finitely many of them. Finitely many sets that look like U cross V to cover A1 cross A2. That's the idea, all right? These are the basics of how you would make this proof work. Like I said, the part that is not quite accurate is this thing right here. The sets in the open cover, they don't actually all have to look like that. These would be what the basis open sets look like. So really you would have to take all of these sets and split them up and shrink them down into a bunch of basis sets, which could work. I just don't want to get into the details of it. All right, so anyway, it is a true fact. If you have two compact sets, then the product is also a compact set, all right? This even works for infinitely many, a product of infinitely many things. Those are very weird, but it's still a true fact. All right, any thoughts about that? Okay, I also wanted to discuss the thing about the subset, all right? This thing, I said the answer is no. If the subset here, right? This is an example where I have a compact thing, and then there's a subset which is no longer compact. If you think about compactness in terms of closed and boundeds, then the fact that the big set is closed and bounded, the smaller set automatically will be bounded because it's inside of the bigger set, if we imagine the bigger set is bounded. So this set B is automatically going to be bounded. I would say whether B is compact or not, really then it only depends on whether B is closed, all right? Because automatically it's going to be bounded. B will be compact depending on whether or not it's closed. And actually that's an important theorem. So this is my second theorem of the day. It says if A is compact and B is a subset of A, and B is closed, then B is compact. So this is like the correct version of that question which I asked at the beginning. It's not true that any subset will also be compact, but it is true that any closed subset will also be compact. Now, for reasons that I said before, this is obvious if you assume the Heine-Borel theorem, the closed and bounded thing. But this is actually true even outside of Rn and even without using the Heine-Borel theorem. So I want to talk about this. A is compact and B is a subset of A and B is closed. This one is not so tricky either. So the picture you should have in mind is A is something like this, and A is compact, and B is inside of A, and B is closed. All right, so our proof, as usual, I'm trying to show B is compact. We begin by saying, just assume there's some open cover of B. So I let O be an open cover of B, right? And, okay, maybe I'll indicate on the picture. B looks like this. I have an open cover of B like so, all right? We need to find a finite subcover of that. The problem which immediately arises, you say, well, I know A is compact. That means any cover of A has a finite subcover. But I don't have a cover of A, I have a cover of a smaller set. So what I would like to do is, my strategy, this is not really part of the proof, but my idea is let's add stuff into the cover to make it cover all of A, right? Because I want to use the fact that A is compact, but A being compact is not helpful unless you have something which covers all of A. So my idea is I want to add stuff into the cover to make it cover all of A. Okay, I would think in terms of stuff to add into the cover, what's missing from this? Why isn't it a cover of A? It's missing, all of these points out here, which are part of A but not part of B, right? Those are the points which are missing. It's missing, I suppose this is still inside my brackets here. It's missing all the things which are in A but not in B. Actually, there's a way to write that as a set. What is that? I want all this stuff like out here. Yeah?
Like A minus B.
Yeah, A minus B. It's missing A minus B. Okay, so can I just add that in as one more set to the open cover? That would be the simplest way to do this, right? You take all the original blue sets plus A minus B is one more set. It doesn't look like a circle on my picture. It looks like, it looks like sort of this ring kind of a shape, right? That's A minus B. Now, if you take all that stuff together, it does cover all of A, because you used to cover B, and then you just take everything else covers all of A. The issue with that is it has to be an open set. All the sets you use in your cover have to be open sets. Is A minus B an open set? I'm here to tell you, we assume B is closed, which means the complement is open, which means A minus B is an open set. And that's what makes this whole proof work. So A minus B, I will say, since this is my real proof now, since B is closed, A minus B is open. I suppose that I mean in the subspace topology of A, but it doesn't, that's good enough, it doesn't matter. Since B is closed, A minus B is open. So if I take O and also this one extra set, this is an open cover of A. All right? It's all the blue guys, that's O, plus also this one red thing. That is now open cover of A. And since A is compact, you only need finitely many of those things, which means you only need finitely many from the O, right? You might, whether you use this one or not doesn't really matter. The fact that all of this can become finite means that the O can become finite, and that's what we needed to show. So this is an open cover of A. So we need only finitely many sets from O union A minus B to cover A. And what that means is we only need finitely many sets from O to cover B, because this other set doesn't have anything to do with covering B. So that means we only need finitely many sets from O to cover B. And that's what I wanted, that's what we wanted to show. That'll do. All right. So that's the end of this business. All right. This is why this guy here. So the answer here originally was No, it's not true that any subset of a compact is compact, but any closed subset of a compact is compact. Sorry, just scroll away from what I just wrote. All right, any thoughts about that? Any questions? Great. I hope you don't mind, but I think that's all I want to say for today. Just looking, we only have like 2 more classes left. So my plan is on the Friday of next week, I want to do, as usual, just like a review for the final exam. As I was looking at the schedule, I think I was going to end up doing all day, a regular class on Tuesday, and then I had only 10 more minutes of stuff for Wednesday. So rather than do that, I figured I'd just stop early each of those 3 days, if that's okay with all of you. I'm not actually fully confident in my ability to predict down to the minute how much time we're going to need, but let's leave it at that for today. I hope that's all right.